Hey guys, so I'm going to be talking about the Sierpinski Gasket, and a lot of you may recognize what it is, but Sierpinski Gasket is this shape. I'm sure a lot of you have seen it in certain places. It is used a lot, but essentially it's actually a pretty simple shape. It's a triangle, and then there's triangles within that triangle, and more triangles within that triangle, onto an infinite amount. So what exactly is it? Essentially, you take the halfway point between each vertice, which would be a side, and you mark a point there, and connect those 3 points within the triangle, and take out that piece. Then you do that for the next remaining triangles, and you do that for an infinite amount of times. So a few things about the Sierpinski's Gasket. It has a visible border, and obviously nothing can come out of that border, so you know it has a finite area. But considering it's technically infinitely complex because it goes down and never really ends, it actually has an infinite perimeter. So something with a finite area and infinite perimeter is certainly odd, and that's kind of the nature of these fractals that we're looking at. So one way you can generate this Sierpinski Gasket is, as I just stated, by doing the middle third, but a strange phenomenon happens when you apply a very simple set of rules. Here I have a triangle, so I can set the 3 points. I'll pick 3 random points. Let's put 1 point here, another point here, and I'll put the third point here. So we have this triangle, right? So essentially, the rule I've given for this is to take the center point, and essentially I say, okay, I'm going to go halfway the distance between that point and one of the vertices at complete random. So I go, and okay, it chose this point, which is halfway between this bottom vertice and the center point. So I do that again. It goes towards that point again, and that's completely random. And now I decide to go towards this point. Okay. And now it goes back to this point, that point, and now it decided to go to the third point. So the pattern that comes from this is seemingly pretty random, and the coloring doesn't really matter. I just assign that to pixel height, so that's kind of irrelevant. So a few things you'll notice. Obviously, since it's halfway between these vertice points, there is no physical way it could actually leave the triangle, so one would expect that it fills up the area. And another thing that should be noticed is that even though you can get halfways between things, there are certain numbers that cannot be obtained. For example, you will never be able to obtain a third from dividing things by 2. Dividing numbers like, for example, 2 by 2, and then you get 1 divided by 2, a half, a fourth. And if you can add halves and such, but you will never actually reach the number a third because it is seemingly infinitely close and yet unobtainable by these means. Following this rule, I'm going to go and let it automatically do it very quickly. And so obviously we see triangle, and you can kind of start seeing like gaps forming. Like I said, there are some numbers that are completely impossible to reach. And as you start looking, you can kind of start seeing triangles within triangles. And the longer this goes on, this actually creates a Sierpinski's Gasket, which is very odd, but it's very interesting. So what you can do with this is a lot of things. This is how I generated the Sierpinski's Gasket, because this algorithm is actually very easy compared to trying to find a half and then going to an infinite level, where instead you could just do this, and oddly enough, the numbers appear pretty apparently. So what I decided to do with this is just a basic overview, but what I decided to do with this was ask different questions, see how far I could push it. At this point, I decided to ask what would happen if I had 4 vertices. This program I have currently that I made can go up to 8 vertices, but right now we're just going to look at 4. So if we look at 4 vertices, you see that a very interesting shape starts to appear. It's almost like there are Sierpinski gaskets making a tunnel, a triangular tunnel almost, and you take the first layer, which I would consider the largest one, and you almost take it and put it in a 3-dimensional space and put it farther back, and it kind of looks like a tunnel, which is very peculiar. And this is pretty much what happens if you put the fourth vertice right in the center. So what would happen if you put it on the outside? So we can try that. And I'll just put it at a random point on the outside. So what starts happening is another very strange thing where you see the self-similarity of fractals really show themselves. You have this sort of, I guess you could call it a kite, and the shape is repeated, and you can see that shape within the shape. And triangles are also taken out of the area, which is pretty cool in my opinion. And so that's what would happen with 4 vertices. So after this, I said, all right, and I decided to add an extra vertice. Let me say I want 5 vertices. So I will put in 5th vertice, and I can try to make a decent pentagon, but I probably won't be able to. If you make a pentagon, the shape that shows up is a pentagon within that pentagon. And then surrounding that are 5 pentagons, and then 3 pentagons around this, and then 3 more around that. And this pattern repeats. And this fractal is actually very useful in many ways, because if you do this with a square, you actually create the antenna that is used in your cell phone, which is very interesting. So after this, I can go and I'll decide to put 6 vertices and see what happens there. So let's just decide that I want my distance to be, I don't know, a half. So what that's saying is that you will go 2/3 of the way. So if I had the division at 1, the distance divided by 1 would obviously be still just 1, and it would go completely between the points, and there would be nothing in between. 1.5 means that it would go, it'd be divided by 1.5, and I think that would mean it would go 2/3. So just using 3 vertices now, just what happens is, I'm going to put this to faster speeds, you get unconnected triangles. Let's see what happens if I decide to raise this number. And let's say I raise it to, 1.75. What happens is you see more of the gaskets. 1.75 is closer, but they're still not touching. So let's say I decide to go to 1.975, very close. They're still not touching, but they're very close. And the fascinating thing about this is that if you think about it, none of the gaskets are connected at all. None of this area that you see is connected to another point in the area, which is very interesting. As connected as it may look, it is not. So as we increase the division, you can see pretty easily that it will probably be more prone to overlapping and kind of filling up space, just because there's smaller and smaller segments it must go in between. So it definitely starts filling up a lot of space, but the triangles are still there. Because if you divide by 3, it means that it can get to a lot more places, but it still can't get to a half, and it still cannot get to a fourth, etc. Of course, I will raise this up to 4, and it really doesn't change much except just add more space. One thing starts to kind of show up, and it's that all the corners, all the vertices are much lighter filled than the center. So I decided to test this to an extreme. So let's say we put our division to a very large number, like 30. So what this means is that it will go 1/30th the distance from this kind of center point to the other points. So what you start seeing, first of all, my center point didn't converge around the center point that I had before, which was a little bit higher and to the right, but it kind of goes to the center of this triangle. And it will take a very long time to get to the vertices. In fact, it'll take an infinite amount of time because it actually can't touch the vertices with a finite amount of time. So now I've set it so when the point is pressed, it starts here. So I'm going to do this slowly, actually, just so we can see what happens. So you see this point, it's coming back towards the center. Rather quickly, actually. This is very slow. You can see it's not filling up space that much. There's a 2/3 chance it would actually go towards the center, and a third chance that it would go back, because we have the 2 other points pulling it towards the center, generally. And then we have the third point, but that's only a third. So to have it go back to the center, there's a 2/3 chance it'd go to the center each time. It really wouldn't take that long, and it did not take that long. Get another decently good rectangle. Need to change my vertices. And 30 division seems to be a pretty good representation of what I'm trying to show here. So once again, I'm going to put it back on this point because I'm too lazy to change that. And it goes back to the center pretty quickly. And pretty much the same thing happens. It's just spread out over 4 points. So let's say I have 5 vertices. And since my 5th one is up here around, it's kind of going to create an irregular shape. And if I have a 5th one in the middle, it will be even more prone to not wanting to separate and take even longer time for it to kind of converge out, just because you have the other point that is a 1/5 chance of it going towards that point, and then just completely removing any progress it had with leaving the circle. I'm just going to finish this video off by showing off some of the stuff that I found, and I hope you enjoyed watching.